In today's video, we're going to be talking about two-body problems. After watching this video, you should be able to develop some strategies on how to solve two-body problems using a systems analysis approach and then an individual object approach. And really, this isn't any different than what we've been doing in the previous lessons where we were drawing free body diagrams, determining the net force on the object, and then calculating the acceleration or whatever it is that the problem's looking for. The difference with these problems is that instead of just one object that we're concerned with, now we have two objects. So for instance, let's say a car is towing a boat. Okay, now we want to know what is the acceleration of the boat and the car, and what is the force of contact between the car and the boat, and that type of stuff. So I'll show you some examples in just a second, but it just gets a little bit more complex. So we're just adding a little bit more of a challenge to it now, dealing with multiple objects at one time. Alright, so this is just some strategies or an approach to handling two object problems. The first is to use something called a systems analysis. Right, and that's usually performed to determine the acceleration of the system. That's kind of the key, is you first want to calculate the acceleration of the system. And when I say a systems analysis, basically what it is you're taking the mass of both objects and adding them together to just make one huge object. So for instance, let's say you have the mass of a car and the mass of the boat, add them together to just pretend it's just one whole object, and then you figure out the acceleration of the system. Then, once you know the acceleration of the system, you can start to look at individual objects and analyze what's happening to each individual object when you isolate it by itself. And this is usually used to determine the internal forces acting between the objects. And as always, a big key to doing this is drawing free body diagrams, labeling all your forces, being real methodical about going about solving these problems. Because if you just try to do it all in your head, it's really hard to get the right answer. All right, so basically we're just going to go through a few example problems together, and that's going to be this video. All right, so it won't be, hopefully not too horribly long. So here we go. Let me change pen colors, something exciting. It says a 5 kilogram and 10 kilogram box are touching each other. A 45 Newton horizontal force is applied to the 5 kilogram box in order to accelerate both boxes across the floor. Ignore friction forces, okay, so we aren't worried about friction forces, and determine the acceleration of the boxes and the force acting between the boxes. All right, so first I'm going to do is I'm going to draw a picture of the situation. All right, so here's a 5 kilogram box, and then here's a 10 kilogram box. And there's a force, which I'm going to call F applied, of 45 newtons to this really this 5 kilogram box. And the 5 kilogram box is pushing onto the 10 kilogram box, okay? So the first thing I want to do is I want to analyze this as a system. And to do that, basically what I'm going to do is I'm going to take the mass of box 1 and the mass of box 2, and I'm going to make it just like one big old box. I'm going to pretend it's one big box, and 10 plus 5 would be 15 kilograms. Okay, so I just basically have taken these two boxes and put it into one, because the first thing I want to do is I want to calculate what is my acceleration, what is A. So now that I have this box, I'm gonna do a free body diagram, and I mentioned it, I believe, in the previous lesson on strategies for drawing free body diagrams. It's basically a two-step approach. The first thing you do is every object, as long as it's not in deep space, will have a weight, okay, or the force of gravity. And so we have a force of gravity going down, F sub g, okay? And to balance the force of gravity, we have a normal force, F sub n, okay? And basically, the two-step approach basically says, 1, draw the force of gravity in, and then 2, ask yourself, what is touching the box? Okay, so the normal force is due to the box being on a floor. It's being dragged across the floor. Okay, so that's one force. Now what else is touching this box? Well, this applied force is touching the box, right? Or creating a force on the box. So someone must be pushing it, or something must be pushing it. And we know that this applied force is 45 newtons, right? Can we calculate the force of gravity? Yes, we can. The force of gravity is basically mass times the acceleration due to gravity on Earth. And so the mass is 15 kilograms. times the gravity on Earth, which is 9.8 meters per second squared. And if you do that math problem, I get a 147 newtons, okay? And this would be going down, all right? And then the normal force is going to balance this out because we realize this box isn't spontaneously accelerating upwards or downwards, so the normal force must be balancing the gravitational force, and so this too is 147 newtons. Okay, so now this should seem kind of familiar to what we were doing last time. I want to know what is the acceleration, and so I'm going to use Newton's second law, and basically an acceleration is caused by an unbalanced force. Is there an unbalanced force in this picture? I think so. I think this applied force is the unbalanced force, and that's going to be in the x direction. So I'm going to write F net in the x direction, so the net forces acting in the x direction, which is just going to be this guy, is equal to mass times acceleration. So what is the net force in the x direction? Well, it's this guy right here, 45 newtons. Okay, 45 newtons in the x direction. The mass of this box is 15 kilograms, and the acceleration is what I'm trying to figure out. So if you do that math, 45 divided by 15, you get an acceleration of 3 meters per second squared. Okay, so that's one thing. The acceleration is done. Check that off the list. The second thing they want to know is what is the forces acting between the boxes, okay? And you can choose either box to work with. You can choose the 5 kilogram box or you can choose the 10 kilogram box. I'm going to choose the 10 kilogram box just because there's going to be one less force acting upon it, and I'll explain that in just a second. So here's my 10 kilogram box, and I need to draw a free body diagram dealing with my 10 kilogram box. Let me just change pen colors here real quickly. So remember, the two-step approach to drawing a free body diagram. First thing you do is draw in the weight or the force of gravity. Okay? Then ask yourself, what is touching this 10 kilogram box in this picture? Well, we know the 5 kilogram box is touching it, right? And so that's going to cause a force, and I'm just going to call that F contact. It's in contact with the box. I mean, you can call it whatever you want. If you want to call it F applied, that's fine. But it's not really so much an applied force that like someone is pushing on it per se, but instead it's just a force of contact with another box. But again, you can the naming piece of it isn't all that important. So we certainly have that happening, that the 5 kilogram box is pushing on the 10 kilogram box. Do we have any other forces in play here? Well, this box is on the ground, right? And so there certainly is a normal force going on here, okay? And we know that this box is not accelerating up or down. So I'm probably going to make the assumption that the force of gravity and the normal force are going to balance each other out. And I'm actually not going to worry about those guys all that much, all right? And the reason why I'm not going to worry about them all that much is because basically we know that they're going to balance each other out. So I'm going to use Newton's second law. F net in the x direction equals mass times acceleration. Okay? Now I'm wondering, what is F contact, right? And F contact is not the same thing as F applied. So maybe I should take back what I said and do not actually use F applied, because that is a completely different number. F applied is 45 newtons. That applied force is happening to the 5 and 10 kilogram box. Right now we're just worried about the 10 kilogram box, and so that's what we really want to focus in on. So F net is the net force in the x direction. There's only one of them. It's F contact, which we don't actually know what it is yet. Okay, that's actually what we're trying to figure out. Equals the mass, which is 10 kilograms, times the acceleration. Do we know the acceleration of the 10 kilogram box? We do. How do we know that? Because we solved for it over here. Okay, both these boxes are connected together and they're both accelerating at the same rate. So I can take 10 times 3 meters per second squared. If you do that math, you should get an F contact force of 30 newtons. All right, and that's how you solve that problem. Okay, so it does involve some thinking. It's a systems approach and basically looking at one of the individual objects on its own. Okay, so first calculate the acceleration, and then you can calculate the force acting between the boxes. If you're not getting it, don't worry. I have another example we can go through. So in this problem, you'll notice that the numbers are exactly the same. It's still a 5 and 10 kilogram box that are touching each other. And a 45 Newton horizontal force is applied to the boxes. The only difference in this problem is that in this problem, I have friction involved. I tell you that the coefficient of kinetic friction is 0.2. Okay, I still want to know what's the acceleration, and I still want to know what's the contact force. Okay, so I'm just going to write that up here. I'm going to write mu equals 0.2, so I have that for reference. And also, I'm going to redraw the situation. Okay, I have a 5 kilogram box and a 10 kilogram box, and they're experiencing an applied force of 45 newtons. Now, the first thing I want to do is I want to calculate the acceleration. And the way I recommend calculating the acceleration is to use a systems approach where you basically take the mass of each individual box, add them together to make one big box. Okay, so I'm going to do that. I'm going to make one big box. And 10 plus 5 is 15, okay, kilograms. Now, this is going to become a free body diagram. A free body diagram involves looking at all the forces that are acting on this box. Okay, so remember, there's a two-step approach to doing free body diagrams. The first thing is draw in the force of gravity, and the force of gravity is always going to be going down. Okay, then ask yourself, what is touching this box, or what is in contact with this box? Well, one thing we know for sure is that this box is in contact with the floor, right? And the floor is going to provide a normal force, F sub n, right? Also, this box is being pushed by something. We don't really know what it is, but something is pushing it, and that would be F applied, and we know that that is 45 newtons. So far this looks exactly the same as the previous slide, but the thing that's new is that I've added the force of friction. How is the force of friction causing this thing to slow down? Well, it's in contact with the floor, so it's touching the floor, and so in actuality this is causing friction to occur. So I'm going to write big F, little f, force of friction. Okay, so this box has 4 forces acting on it: the force of gravity, the normal force, the force of friction, and the applied force. All right, I'm going to calculate the force of gravity first. 15 times 9.8 is 147 newtons, pulling down. The normal force is going to counteract that or balance that out. So a normal force is 147 newtons. Okay, and the reason why I can say that is we just use common sense and our noodle to realize that this box isn't spontaneously accelerating upwards or downwards. Okay, it's just staying on a flat surface, and it basically tells us that it's moving horizontally across the floor. Okay, now the force of friction, how do we calculate that? Well, remember, the force of friction is equal to mu times the normal force. Okay, mu times the normal force. And so that's why we needed to calculate this normal force. In the previous problem, I may have said, Venny, why are you making us calculate the normal force and the force of gravity when it's not really necessary? Well, in most problems, you probably will be dealing with some form of friction, and so you will need to calculate the normal force. So anywho, let's put some stuff in here. Mu is 0.2. The normal force is 147 newtons. And if you take 0.2 times 147 newtons, I get a force of friction of 29.4 newtons. You'll notice I put the forces right on this free body diagram. I personally like to label my free body diagram with all the forces so I can pretty clearly see what everything is. And again, a clearly labeled diagram I think is worth $1 million. And I'm a relatively sloppy writer, so I think you guys probably can do a better job than me. Anyway, now that we've done that, we can now start to finally use Newton's second law to calculate the acceleration. Let's use magenta. So my forces in the in the y direction seem to be balanced, right? We have a normal force of 147 newtons, and we have a gravitational force of 147 newtons. So I think we can not even worry about in the y direction. There's no acceleration. But in the x direction, F net x equals mass times acceleration. Now, what are my net forces in the x direction? Or what I should say, what are my forces in the x direction? Well, we have F applied and the frictional force, right? These two forces are fighting against each other. So I can write 45 minus, 29.4 equals the mass, which is 15 kilograms, times A, all right? And if you do this math right here and this little bit of algebra, I get an A of 1.04 meters per second squared. And that is my acceleration, okay? So we got one thing done. We determined the acceleration. Now, we're going to determine the contact force. And again, you can pick either box, but I'm going to pick the 10 kilogram box, and the reason why is there's just one less force acting upon it. All right, so if I take a look at the 10 kilogram box, put it right here, and I draw another free body diagram. Let me just change pen colors here again so that we can do something different. And I draw a free body diagram. Remember, two-step approach to a free body diagram. One, draw on the weight, or the force of gravity, okay? And then two, ask yourself, what is touching this 10 kilogram box, okay? Well, the floor certainly is touching it, right? And so that's going to provide a normal force, F sub n. It is in contact with the 5 kilogram box, right? So it's going to cause a contact force, F contact. Also, we know that this 10 kilogram box is in contact with the floor, so beyond the normal force, it's going to experience a frictional force, okay? And so it has 4 forces acting upon this object. Now, you may say to yourself, Venny, why didn't you pick the 5 kilogram box? The reason why I didn't pick the 5 kilogram box is because beyond these 4 forces, there would be another force in which the 10 kilogram box would be pushing back on the 5 kilogram box. And since we haven't talked about Newton's third law yet, I'm not really going into that right now. I think it'll just cause more confusion than it's worth. But once we talk about Newton's third law, if you want to ask me in class about it, we can certainly talk about it then. Okay, but for right now, I picked the 10 kilogram box. Basically, it's the one that's furthest away from the applied force. So if you can like imagine some little hand here pushing these boxes across the table. Basically, you want to pick the one that's furthest away from the thing that's applying the force, and that will give you the least amount of contact forces, if you will. And again, if you just keep in mind that the two-step approach to a free body diagram, 1, put in the weight, 2, ask yourself what is touching that object, then you really can't go wrong. If you think about everything that's touching that object and how it would create a force upon it, you should be able to get a pretty good free body diagram. Okay, so back to work. What is the force of gravity on a 10 kilogram box? Well, 10 times 9.8 would be 98 newtons, right? 98 newtons. So if the force of gravity is 98 newtons, the normal force is 98 newtons, okay? Now, what is the force of friction on this guy? Well, the force of friction is just this formula right here. Force of friction equals mu F sub n. And mu is 0.2. That hasn't changed. F sub n is 98. And if you do that, the force of friction turns out to be, I'm going to write this right down here, 19.6 newtons. Okay? Now, the question is, what is the contact force? That's what we're trying to calculate here. So I'm going to change pen colors one more time just to really change things up here. Let's do white. So I'm going to use Newton's second law to figure out the contact force. So I'm going to have F net in the x direction equals ma. Now, what are my net forces in the x direction? Well, I have the contact force, which I know is going to be bigger. How do I know it's going to be bigger? Because the box is moving. It's going to be bigger than the frictional force. So F contact minus the frictional force, which is 19.6 newtons, equals the mass, which is 10 kilograms, times the acceleration, which we calculated already, right? The acceleration is this bad boy right here, 1.04 meters per second squared. And if you do all that math, that you do a little bit of the algebra and all that good stuff, you should get a contact force, F contact, of about 30 newtons. That takes care of this video. I will see you guys next time.